Yeah. Okay, so let me start with apologies for the delay. So it's an open talk. Each one, each person is responsible for what she's saying, and it will be recorded and available. So if you don't want to say something, don't say it. And second, that this is kind of mixed thing. It's kind of a talk about some achievement of this artificial intelligence mathematics, and also a kind of interview. And I hope that we will be able at some point to ask different questions. At least I have a lot of them, but let's see how it will go. And as usually, we encourage people to, if something is unclear, to ask immediately. But if it's too many things, maybe we have to switch. Today we have not unexpectedly, but exceedingly many people. So how it will work, we'll see. Okay, please, Yury Kudryashov, a winner of some Olympiads long ago, and then working with Lean, and now trying to use it in artificial intelligence with some company.
The company is doing business as Harmonic, uses some strange legal name. And before I start the talk, I want to say that more than uh, almost 4 years ago, my country um started full-scale invasion of Ukraine and kills Ukrainians every day. And I wish Ukraine all the luck in repelling this invasion. Um, and sometimes I'm doing whatever I can to help them. And now, while the talk is called Lean and AI, and it looks like many people are interested in the AI part, I am more of an expert in the Lean part. So my slides are about Lean. Um, Possibly I will skip some of them if there will be no
Okay, once we had
questions.
a talk about Kok, and it was first it was Stepa Kuznetsov, and then Vereshchagin tried to explain what Kuznetsov said, and I still not succeeded in this, but at least we heard something about this.
Yeah. So, first, what is a proof assistant, also called interactive theorem prover? A proof assistant has some input language. It can be something that looks like a programming language, or it's indeed a programming language. And it has an interpreter or a compiler that reads a file in this language and verifies it for correctness. In particular, and there can be some automation tools to help the users. In particular, it does not prove theorems for you. Usually, in order to write a theorem in a theorem prover, you need to write maybe 2x, 3x, sometimes 10x more text than on paper. This factor changes every month with better automation. Different proof assistants use different underlying theory. I'm working with Lean, which uses what is called dependent type theory. But for most users, this is more like an implementation detail. Uh, okay, the language looks different, but uh, what's important is that different proof assistants are incompatible. So if something is formalized, for example, in Coq, you cannot uh, like spend 2 minutes and have it in lean uh, for different reasons, from incompatible basic theories to incompatible like main libraries. And as an example of what code in lean looks like, here is the statement
You're,
of the
sorry, can
Poincare recurrence theorem. Yes?
can you share more details why you cannot convert one proof from one of these to another? So there is no tool, so there is a theoretical reason for that. I mean, we cannot do that.
Uh, one issue is that they use different underlying theories, and if you more or less if you convert, then the converted version will use different real numbers, different natural numbers, etc., etc. Even if you write such a tool, it's hard to. Uh, it would be useless, like with the main mathematical library for the other language.
But still, there is some reasonable reason certainty that if you prove in lean, you prove some theorem with the existing libraries about natural numbers or real numbers or whatever, then you can convert this proof into set theoretic proof with some additional axioms. So it's not the people do not question whether the real number are different, are correctly represented or not. People agree on this, yeah?
Uh, yes, there is a PhD thesis that tells precisely what theorem do you need. As infinitely many unreachable cardinals, uh, something
I
like
heard
that.
something like we need them to get some Grothendieck worlds or whatever. So, but it's very interesting from the logical point of view. But maybe we will postpone this
Uh,
discussion.
yeah, but yes, uh, real numbers. There is no question. Oh,
Sorry,
what?
there is some strange noise. I don't know who is making it, but okay, now it's better.
Okay. Uh, so people agree that like
Ensuring solution.
mainstream libraries in these languages correctly define naturals, integers, reals, etc.
Yeah.
Uh,
So
but
this is not thing that people don't say that look, you proved, I don't know, formalized some Fermat theorem, but we don't trust your implementation of natural numbers. This is not an issue typically. People don't complain.
no, this is not an issue. It's just there are so many design choices in mainstream libraries for different languages that are done differently. For example, MathCom for Coq uses intuition. Tries not to use axiom of choice whenever
Mhm.
possible, while mathlib for lean uses axiom of choice whenever uh, it feels like it will be more readable.
Okay,
Even
okay.
if we can avoid it with by writing it, I don't know, another 200 lines of code, we don't do it. And uh, the statement of Poincare-Recurrence theorem uh, should be more or less readable for a mathematician. Uh, uh, this is this exists mem image mem is the non-trivial part. It says that if F is a measure preserving map from some measure space alpha to itself, and this is a finite measure, mu is a finite measure, and S is a measurable set of non-zero measure, then there exists a point and a non-zero iteration such that X comes back. And once you have a theorem like this, you can prove it. Proofs,
But
some
let me
proofs
check that I
are,
understand correctly, that all definitions of what measure is, of this and that, are just in this library which called measure theory and is mentioned
yeah,
here. Yeah?
it's in it's in the library called MathLib. Uh, eh, of course, in order for this code to work, you need to define all these.
Yeah. So this is hidden by some syntactic sugar, but they are under the hood. Everything is there. Yeah.
Yes, and if you open, I copy pasted this into slides, but if you open the original code in the repository on GitHub, then you can click on each of those measure preserve and measurable set, etc., and go to the definition.
And for example, if you look at, I don't know, about omega additivity, it's somewhere there explicitly. It's just,
Yes, if you click at measure, then it says that it's a function with this and that axioms
Mhm.
about it.
Okay.
What is conservative?
Uh, Conservative is defined right here. It says that it's quasi-measure preserving, which is not defined here, which means that the pre-image of a null set is a null set. And then it says that a conservative system is a system that satisfies the conclusion of Poincare-Recurrence theorem. It's just so Poincare-Recurrence theorem, in terms of this conservative, a Poincare-Recurrence theorem says that measure preserving map on a for a finite measure is conservative.
No,
So
I think
the standard word definition here represented like structure and extents. Yeah?
Yes, extends means that it adds all the fields from the structure quasi-measure preserving, which is not here.
About usually we use word definition, and you also used word definition. So instead of definition, we use different red emphasized words.
You can use there is keyword definition, but this structure is another way to give a definition.
Okay.
No, just a basic, simple question. If the theorem is in the second line, why we don't need lines 3 and 4? Why? It's just.
It's just a way to it's just a way to show other syntax features. For the main theorem, you don't need
So
those
the last
conservative.
theorem is a different theorem.
Like every mathematical theorem may have many formalizations.
So the last line is for formalization of the same Poincaré recurrence theorem or something else.
It's a formalization of the same Poincaré recurrence theorem, but in terms of this new definition conservative.
So it's just an example of two kind of different statements which are essentially equivalent. There is no mathematical difference.
Yes.
No, we don't understand the details, but probably it's not needed to understand for now.
Yeah. I do not expect you to understand what's written here in the proof. More or less, it follows the standard proof. If we had more time, I would go over it line by line.
Yeah.
I specifically chose a proof that is more or less well written. There are much more cryptic proofs in MathLib, especially when someone tries to prove something in the least number of lines instead of optimizing for readability. What it says that first, this have A means first we prove this fact that all the preimages of M are null measurable sets. By convention, we use measurable sets for Borel sigma algebra and null measurable sets for sets that are Borel up to a set of measure 0. That's what's called measurable sets in many courses, but we use this convention. And then the measure of each preimage is the measure of the set, and then measure of the whole space is less than the sum of all these measures, etc., etc. Then it chooses I and j less than n such that they are not equal and the preimages have non-empty intersection, etc., etc.
So what I think do you want to say that with some experience you can more or less read this proof and translate normal mathematical proof in this language? It's not just something completely different obtained by some computer procedure. It's just a normal proof written down by an expert in Lean.
Yes.
Yeah.
Yes.
Yeah. Okay. Then we don't understand the detail, but have to trust you.
Yes, this proof is handwritten. I think I wrote this proof a couple of years ago, maybe 3 years ago.
Yeah.
And when you open it in an editor that supports Lean, VS Code with a plugin or Emacs or NVim, then at each step it shows what is given and what do you want to prove. And as you step through the proof, both parts can change. And more or less, with this extra information, if you read a Lean proof in an editor that supports it, and you step through the proof, then a way to translate it into a mathematical proof is to write down some of those halves as next statements and put obviously between every two steps. Usually, whatever takes 2 to 3 to 2 to 10 lines in Lean should be obvious mathematically. Not always, but in many cases. There are some large theorems formalized in different proof assistants. Probably four-color theorem and Fate-Thompson theorem and Koch are maybe most famous. There are other things like the fact that the Mandelbrot set is connected was recently formalized, and it was quite surprising. I know more or less nothing about Geoffrey Irvin. He came to the chat room, said that, hey, I want to formalize something about Mandelbrot sets, asked a few questions, and then in 3 or 4 months, he comes back and says, oh, I formalized connectedness of the Mandelbrot set and of its complement. It was
and people agree
impressive.
that indeed what the statement that he proved is really means the connectedness of the Mandelbrot set. So it's not a question.
Yeah, I opened the repository and verified that the statement is what it claims to be.
Yeah. So it's a bit paradoxical. For example, now we know from the first line that four-color theorem is provable in set theory with some large cardinal axioms. But okay.
Yeah, and and recently, for example, Terence Tao came to our chat room, said that I have this work that is still pending review, and I want to formalize it. And he provided a very detailed human readable proof. And I think the whole proof, it was, I don't know, 20, 30 pages long, but it was formalized by volunteers in 2 to 3 weeks. Even so, after this, we know that there are
how
no.
Many volunteers was there?
Sorry?
How many volunteers was there? I mean, how many persons per hour?
In that particular project, I don't know. I did not participate in this particular project.
Yeah, but more like 4 than 4,000, I guess.
I think more like tens of.
Actually, I heard a talk of Sanjeev Arora, who said that recently, with the help of AI, they did something with some other result, which I forgot which was exactly the result, and they did in a month something that they planned to do for a year or something like this. I don't know whether you know what he's speaking about, but
prime number theorem recently they.
Yeah,
no, I think recently, it was kind of.
Recently, some stronger version of the prime number theorem. First, it was formalized by humans, and it took a long time. Recently, some AI company, I'm sorry, I don't remember which one, I can look it up after the talk.
Okay.
They auto-formalized a human readable proof very quickly. They fed it to their system and it auto-formalized it.
Yeah,
Kirill in days said or in a
project Gauss. So we can later Google it. Okay.
And why bother about all this? One reason is correctness. for example, this theorem is incorrect. Let F be a map between complex normed spaces. If let U be a bounded non-empty set in the domain. If F is complex differentiable on U and is continuous on its closure, then the norm of F achieves its maximum on the closure of U at a point on the frontier of U. This statement is incorrect, but I would not be surprised if a statement with this or similar missing assumption would be accepted for publication. One of the ways to fill in the gap is to assume that the domain has finite positive dimension. It breaks both for the domain being a single point and for the domain being an infinite dimensional space. There are other ways to fill in the gap, but anyway, when I was formalizing complex analysis in Lean, I started proving this theorem. What you see on the screen is the correct version. It says that it uses E and F instead of V and W. It says that if E is a normed additive commutative group, which is a normed space over C, and it's non-trivial. Non-trivial means that it has at least two elements, and it is finite dimensional, and F is any normed space over C, then this theorem holds. If F is a differentiable on the set and continuous on closure of the set, on U is bounded and non-empty, then there exists a point on the frontier such that norm of F takes its maximum value on the closure at this point. First I forgot about, at least I forgot about non-trivial. I don't remember if I forgot about finite dimensional. But then I started writing down this proof and just some steps didn't work. And I had to add those assumptions for the proof to be accepted by the system.
So the story is not about somebody published this incorrectly and then while trying formalizing you found the error. It's just it could be that somebody forgot this and
yes.
yeah. But you tried to formalize and you see that something is missing and you were able to identify what is missing and so
on. Yes.
Okay.
And a story closer to what you said is Turnstile wrote that as a consequence of his Lean 4 formalization project, he found a small but non-trivial bug in his paper, which was under review, but this was kind of a bug that I would not be surprised at all if it would be missed during review process. It was something like he cared about large values of n, but he stated the theorem for all n, and it failed like for n equals 1. But worked for n greater than 1 or something like that. Since nobody cared about small values of n in this context, probably it would be accepted by a reviewer, but it was caught. Another reason why bother about formalization is improved search. For example, you can search all theorems that assume that some space is a Hausdorff space, or all the ways to prove that something is a Hausdorff space that are known to the system, or something like that.
But this depends on the fact that in the library, the Hausdorff's notion is called Hausdorff. If in the library it would have another name, it will not tell you that this actually usually called Hausdorff, yeah?
Okay, you need to know how something is called in the library, yes. You can have some extra tools that translate to English and back again. Usually, these tools are a bit less credible in the sense that they can make mistakes. For example, if something says finite, it can be a finite model. We have definitions model.finite and finite in the root namespace. And these in English language search can make mistakes in situations like that.
But we don't need formalized proofs for that. Actually, we just need to formalize statements.
Yes.
Kind of search.
No, I mean, improved search can, if you already prove a lot of theorems and give a lot of definitions, then in terms of these definitions, you can search, I don't know, I can, I can go to Google and, for example, search for, oh, yeah, there is an example. We are looking for square root of a number multiplied by square root of the same number, and it finds this theorem that says that if x is a non-negative number, then root x times root x equals x.
Yeah, but this is more like a text search than the logical inference. It's just useful tool without claims of any.
Yeah, it's more like I mean it's inspired by Hugo in for Haskell.
Okay, yeah.
So it's but it's really useful if you know more or less what are the assumptions of your theorem or what are the conclusions, then it's useful.
Oh, I have an egoistic request. Can you look
Yeah.
for something called upcrossing inequality? Does it know anything
If you
about
want to
upcrossing?
search by name, maybe linsearch.net can do it. I don't remember.
It's not really important, but
I mean, oh no.
okay, forget
Is
about
it
it.
done? Okay, no, not right now.
Okay.
One of the servers that was doing this English language search was shut down recently, and I did not update in my head what should I use now. I mean, except for a full text search in the repository. And sometimes you add an assumption because you think that it will be useful, but then you never use it in the proof. And there are tools, automatic tools that will tell you, that will warn you that you have an unused assumption. And this actually helped me maybe a couple of years ago. I removed an assumption of some space being a Hausdorff space from one of the lemmas, and then compiled the library, and while compiling the library, this linter was warning me every time a downstream lemma no longer needed a Hausdorff space assumption. So it could be useful. If you are in the middle of some proof and you read it in an editor that supports Lean, then you can click on every variable or every term and jump to the definition and see what exactly does it mean. This also could be useful. And I can definitely imagine moving some boring details about some technical lemma to a computer verifiable file and explaining the idea behind the lemma instead. Because quite often you have a choice between explaining the idea so that it makes sense and it's useful to, I don't know, prove something similar, or write down an actual detailed proof which can be much less illuminating. Or you have some computation that nobody actually cares about except for it being correct. And moving such things to it.
Yeah, but then these explanations are not checked by anything. They are just
yes, but if you state the lemma, you prove it in Lean.
yeah.
But for humans, you explain why this lemma should be true, and say that the
It's
details are written
useful,
in Lean.
but okay.
Of course it has its own pros and cons. And of course, AI-generated proofs more or less imagine that you have AI systems that produce proofs in if they produce proofs in natural language, then there is no easy way to verify its correctness. But if they produce proofs in Lean, then you can verify them on the fly, discard all the incorrect proofs, and find the correct proof. So if in this analogy of I don't know, monkeys writing War and Peace, accidentally writing it, imagine that you have a second system that can look at paragraphs and say if they look like something resembling War and Peace, then producing War and Peace is much more probable.
Yeah, what, by the way, I can repeat what said Aurora about this thing, that he said that usually these artificial intelligence systems are learning on the human input or human grading and so on. And this is a limitation. But there are several domains where they are not necessarily restricted to this. For example, when they learn how to play Go, they don't only study the parties played by people, but also played against other programs. And thus the success is just winning. And here also there is with Lean and or other provers, there is a way to make learning human independent. The machine may just learn how to produce something which is approved by Lean. And this
yes,
theoretically can be one barrier less.
and practically.
Yeah.
Yes. And what all those AI companies, including Asset Harmonic, including DeepMind at Google, etc.,
Yeah.
are doing, we are generating lots and lots of those lean goals and let let the system try to prove them, where proof means produce a text that is accepted by lean compiler as a proof.
Yeah. So, but we don't recall that our seminar is open. So, like in Soviet time, на военном деле нас учили, вот данные ракеты там такой-то по открытым данным зарубежной печати. So what other people at least say about this? Okay.
Yeah, I'm in a bit of a difficult position. I cannot give too many details about our work, and I
But
probably
you
should
can,
not
yeah.
promote competitors. So I can give only very
But you should
vague ideas.
disclose their secret, so it's not.
Yeah.
Okay.
I don't think that we have time for Carrie Howard's correspondence.
Yeah, but this is something which probably some of us know, because in logic
Yeah.
it's called the realizability or finite problems of Kolmogorov-Medvedev, but this is kind of other story.
Yeah. And one more thing that makes those systems like Coq and Lean more trustworthy is that there are two parts of the system, kernel and front end. And front end is responsible for reading the file, understanding what each symbol means, executing automation, etc., etc.
But correctness doesn't depend on its.
Yes, and then it provides those terms for Carrie Howard correspondence that are verified by the kernel. So as the output of each definition or a theorem or something, it produces this term that is sent to kernel for verification. So if you have a bug in your tactic, then it will not make the system accept a faulty proof. And if you want to decide whether you trust the proof, you need to verify the kernel, of course, which is like once per release or something like that. The definitions involved and the axiom, and whether you want to use the axioms used in the proof, which is usually a much smaller amount of code rather than everything involved in the proof. You can, for example, if you, I don't know, if at some point someone, I know that Kevin Buzzard is working on this, don't know about the progress. Someone formalizes Fermat last theorem, then clearly verifying the statement is much, much easier than verifying all the theory involved. And if you can
one do not need to verify whether the algebraic geometry notions used in the proof are correctly implemented in the libraries. They are just tools, and if something is correct, then it works.
Yes,
Yeah.
even if some definition from algebraic geometry does not follow precisely what is usually written in human texts, if it allowed us to prove Fermat's theorem, then we have a formal, we will have a formally verified proof of Fermat's theorem at this point. Of course, if the project succeeds, it's quite a lot of code to write. The library, sorry, I accidentally clicked. The library is on GitHub. It contains almost 7,000 files, goes from definition of a group, monoid, etc., to modular forms, I don't know, harm measures, schemes, Lie groups, etc. It has more than 1,200,000 lines of code, more than 300,000 lines of comments.
Not much.
I would not trust those counters of definitions and theorems because many maybe like 90 to 95% of them would not be called definitions and theorems by mathematicians. They are something auxiliary or something so trivial that it should not be called a theorem. But I don't have time to go into details. Currently, the project has 650 contributors, and maybe a year ago it was more like 300. So the project definitely grows in the number of contributors. Many of them are some students who took a course on Lean, contributed one or two pull requests, went away and never came back. But nevertheless. And on a modern hardware, it takes from 20-30 minutes to 3 or 4 hours to verify all the proofs in MATLAB from scratch. It highly depends on hardware. I don't have time to go over stuff I contributed. As a last example, this is one of the problems from IMO 2025. It kind of duplicates. I should have not added this definition. Okay, it says that a function from positive natural numbers to themselves is called bonza if for any pair of natural numbers b to a has the same remainder modulo f of a as f of b to f of a, and it overall bonza functions, what is the minimal no the what is the maximal linear growth, what is the minimal c such that f of n is less than c times n for all bonza functions and for all natural numbers n, and the answer is 4. And this summer our system was given this main theorem without this definition. I should have not copied these 2 lines. It was given this theorem, main theorem, and it produces about, I don't remember, maybe 1,000, maybe more lines of code of a proof. Of course, it also tried many more lines of code and rejected them in the process, but it produced some formally verified proof.
But here, for the first time, you speak about combination of this prover with some other tool which tries to generate to find the proof, yeah?
Yes.
Before you
Yes.
spoke about people who convert the proofs into some formal proofs. And here you didn't have any numerical proof, or any readable proof, or anyone who knows the proof and tries to help formalize it. It's just a system which didn't know about this problem started to work the theorem and found the proof.
Yes. Yes. And here I think all I can say is that it tried a lot of it made a lot of attempts, and one of them succeeded.
Yeah. So maybe at some other occasion we can collectively suggest some problem, and then probably not so difficult one, probably like this one, but then you can write it into Lean and then see whether your system is able to find the proof, or it's too expensive to try.
It depends how far away is your problem from what is already in MATLAB. Like, I mean, I can try what is cheap and what I am allowed to try without any approval. But the harder the problem and the further it away from MATLAB, the larger the probability that it will fail.
Yeah.
Okay, so
there was a lot of noise about publications, even in Nature and whatever, about artificial intelligence, so-called tools to solve IMO problems. Is this announcement the first when it was not this general artificial intelligence stuff, but specific Lean or Coq or whatever prover to be used in IMO?
There were more or less two kinds of announcements in the last 2 years. 1 to 3 years. One was about geometry problems. Geometry problems don't use Lean for reasons I don't want to discuss now. More or less not enough support in MATLAB yet. And they used this alpha geometry and what we recently open sourced called Euclid. They use some domain-specific language for geometry problems. For algebra, number theory, combinatorics, all AI companies that I know of either disclose that they use Lean or avoid answering this question, and I suspect that they use Lean behind the scene, even if they deformalize the proof afterwards.
Yeah, but the question was, they usually announce that they use some kind of their artificial intelligence tools. Let's have Lean aside. But you say that Lean is the only tool.
No,
But
Lean is
No,
not an
choice-
artificial intelligence tool.
Artificial
Lean-
intelligence is used by them, by this company, which Europe represents, for finding the proof. It's really used. It's Lean is just kind of
Language.
checker, but there is
Yeah,
artificial intelligence involved.
They were using large language models. Lean does not use any large language models. It uses only this database you described. Okay.
You can think about it this way. You can think about Lean as a sort of a compiler, as, I don't know, a C compiler. And we and they, you or Haskell or whatever. The AI companies use large language models to write source code for this compiler. And then this compiler, all this compiler does is it verifies that this code compiles.
Okay, usually you need not only code that compiles, but which is correct, but here it verifies everything.
Yes. It verifies that that it produces a proof of this particular theory. And it doesn't use any unexpected axioms.
Yeah. So their large language models were not using this, zillions of text, but used only a limited amount of solutions of different problems of IMO, etc. So they used only mathematical texts, nothing else. So
not clear. Maybe they just were learned on everything and then applied to find proofs.
Sasha, this is my question. This is exactly my question. We're trying to understand. Was it enough to use only mathematical texts and then to use something like Lean to and their networks and neural networks and whatever to solve IMO problems? Or do they claim they are using something much more bulky, a lot of different texts? So the issue is it enough to use only some mathematics to make a source for compiler, etc.?
Here I will answer based on what alpha proof people published in order to definitely not disclose any secrets. They used Gemini, so they used this huge Gemini model and specialized it to produce better Lean code using
retrained versions on general data.
They trained both on human-written problems, and they also auto-generated some problems.
No, but did they use the model which was trained before on all the text on the internet not related to mathematics too?
Yes. They used their Gemini model and then specialized to mathematics.
Okay, so now you present us the first case where only mathematics was used to solve mathematical problems.
No, this is not claimed. Since I don't know any secret, I could suspect that this is not the case, but Yury cannot comment on it. But I guess it's not claimed, and this is clear.
I cannot disclose. My NDA does not allow me to answer this question. I'm sorry.
Okay.
Okay, but let me just say that you have a very good model which works generally somehow, And then there is a general theory that it's much easier to pre-train. You use a model which is trained on some data for your special domain. And so for me, it would be quite natural if they tried some general model and then try to provide some additional training on mathematical texts. And so I really don't know, and I haven't discussed this with Yury, so it's not a disclosure of anything. It's just what I heard in other contexts and what seems reasonable to me.
Yeah,
Okay, but
fine-tuning.
So I have a question.
Yeah.
Just I just read there are 16 slides of 17th. Let's look at the 17th
I don't
slide.
remember. No, it's some speculations about what could we use AI for, like formalizing existing papers. For example, you are working on
Not existing mathematical results, but existing mathematical papers. That's what you say.
Yes, like one of the reasons why Lean is not useful for research right now is because while Mathlib is huge, it's a tiny fraction of human mathematical knowledge. And if we want to make Lean useful for research, we need to formalize, we need to grow it maybe at least 100 times more. And auto-formalizing texts using AI, possibly with some human review of the definitions or something like that, I'm not sure, could be a path forward. And another thing is, imagine you are expert in one area of mathematics, but for some reason, for your current research, you need a result from another area. Then AI tools and those formal search tools can definitely help you find the relevant theorems that you could use. But for this, it needs to formalize lots and lots of pre-existing knowledge first.
Okay, so let me say that now somehow our first part is finished. We heard the talk, and now we want to proceed to the interview part. But first, I think that once in I don't know, in 2 weeks.
I have a question about the talk.
Okay. If it's question about something specific, let's try it now.
Yury, how much cost the theorem you showed in the previous slide? How much it costs to prove it? I mean,
in terms of what?
Electricity, or I don't know.
No, I guess this question is out of possible. So if it's not published in for other systems,
we do not disclose these. Indeed, this would be the right metric to compare different companies, but since other like we published our announcement later than other companies, we decided to wait a little bit after humans' achievements are celebrated. Some companies announced before the closure ceremony of the IMO, which is not very nice.
Yeah.
to humans. We decided in advance to do it later. And since other companies did not disclose the amount of compute they used, we don't disclose it either.
Okay.
Sorry.
Okay. So are there some specific short questions related to the talk now? So if not, I guess once, maybe in 2 or 3 weeks, we will, if Yury agrees, it will be nice to have a kind of a session when we can try just online. We suggest some. We see this in action somehow at the extent possible by the NDA and so on. And this will be very interesting, but let's now ask some specific questions. So I have some, but maybe it's better to start with others. So if someone wants to ask the question, just try. Okay, let me then start with the question. So
I mean,
recently,
I can try to ask, but I don't know. But it's just sort of maybe, I don't know if there is. So if I want to train a model that transforms a language model that transforms an informally written statement into a formal statement in some, well, formal system like Lean. So, I mean, there is a obvious obstacle because it has to be verified by humans, right? It's not like if I have a proof written in a formal statement, if some model produced me a proof, then Lean can check if it's correct or not.
So you say that still people are needed to check that the statement is transformed correctly.
So I don't know. My question, I don't know how could we try to maybe, is there a chance to automatize, well, like to make it automatically also somehow, sort of generate maybe randomly statements that we know what they should mean, that I don't know, that they are correct mathematical theorems, and then train a model to transform them into how we would do a data set.
Auto-formalization of statements is a good non-trivial goal, and indeed there are quite a few obstacles, and the main obstacle is that you cannot completely automate the training in terms of in the same way as you can automate the training of the model that provides proofs, because there are lots and lots of ways a model can fail and provide something that looks very similar to what it should be, but not.
Okay. So I have another question, more specific. So recently I tried to I took a problem from some blog about some graph of sine, which looks like several graphs of sines and something like this, and then I asked the computer to find the period of this seemingly graph, but doesn't matter now. But then I asked it to ChatGPT, and ChatGPT did something, give me some incorrect answer. I pointed out that it's incorrect, and then it gave some correct answer. My question, during this process, did it use some kind of tools like Lean, or it's completely on the level of language models?
My guess
It's not about your system, of course, so you can guess freely.
My guess is that they do not formalize mathematical questions at the moment.
Yeah, so all the reasonable things they said just on the level of language models.
Yes, I think yes.
This is very impressive, actually.
Yes, yes.
Yeah.
For us, one of the main reasons why we choose to use formal language is the following. Imagine that, I don't know, in a year or two or three, some large language model produces 300 or 500 pages of text claiming that it proved some big theorem. I don't know, ABC
it's completely obvious. It's very. I think everyone now understands why you should do this. What is not obvious how you can avoid this, but still. Okay, and another question about the same experiment. So while I asked this ChatGPT thing, he or she or it thinks for several seconds or minutes maybe, and then it seems that there are some kind of stages. It says something that now I'm trying to do the blah 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 blah, or finding this, or it makes some comments. But what are the? Do you understand what are the stages? So several years ago, we saw have a talk when people, Maxim Ushakov, explained that what they do is they predict the most probable token using some machine learning and something like this. This is just kind of one stage thing. And now it seems they do several things. Can you explain or guess what they are doing actually?
One of the things they are probably doing in those thinking models is that actually they this thinking model is a front end for a script that invokes the simpler model several times with different prompts. And you can do things like first of all, disclaimer that while I'm working for an AI company, my AI knowledge is very low.
And
I
you're
worked on the
guessing
lean
about happening
part.
in other companies, so it's very real.
Yeah. I mean, my general AI knowledge
Yeah. Mhm.
is much lower than you would expect from a person working at an AI company. I know a lot about lean, much less about AI. But you can do things like invoke a model. And I saw some traces of it in when I used Gemini to produce code. Just I was lazy and wanted to have it fast. Um, you invoke a simple model, and then you take the output of this model and feed it to maybe the same model but with another prompt saying that I don't know, this answer was produced by a student, you're a professor grading it. Tell you your opinion, show mistakes, and it shows something.
Yeah, and for example, for example, in my case, when I ask something, it provides a graph of some Lissajous curves and counts the intersection point. So I guess it actually called some program, some interpreter of programming language to produce this graph. It's not on the level of language model.
Probably yes. I don't know how do they deal with graphics.
And another question. So
can I answer
asked,
the previous one shortly?
Yeah.
If that's okay. So if we're talking about thinking or reasoning models, the main thing we should do, it was trained on a little bit other data, but mainly you can, for example, visit the cloudy.ai and it will show you what it's doing between steps. So mainly it just talks with itself for another 10,000 tokens. So let's say you train the model on the data, which included all thinking which person is doing at the moment when you ask a test. And after that, we found out that if the model will spend some tokens producing some text in the style, okay, user asked me to draw a graph. I want to, and blah, 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 blah. In this case, because it was trained on better data where the thinking was made, just by language large models generating the next tokens, the answer just simply will be better. That's one thing which is happening in if you extend thinking will if you mark the checkbox extend thinking. The other thing which is popular right now with AI, with what you can give the AI ability to call tools and to receive responses. So for example, in some cases, AI can generate some Python script, run it on their own, and then see the results which were happening and include them in context window. So basically, sometimes it can run the Python script in the steps and do something. But mainly just a reasoning can already really extend the ability of LLM by just predicting the next token better because it's trying to create a longer text than it's showing to you. And in this text, it uses this generated text as a context to answer your question. You can see the process of generating this like middle tokens if you will ask Claude about something and it will be showing something like I'm thinking about it, and you can click on this text and it will extend what is happening right now, what text it is generating, and just before showing you the real answer.
Okay, other questions? So I have some, no, there are some specific questions about this AI tools. Probably, as you explained, it's not you who should be asked about that, but just a more general question about the situation in the industry. So, yeah, you have a question, Mansoor, please.
Yes, sorry, maybe
Yeah,
more related to lean. So my question is, can lean, or I don't know, maybe lean with this AI tool or something, help with counterexamples? So for example, you showed us the wrong theorem statement. So is it possible that this lean or AI tool will say, okay, you have wrong statement because this function will not this concrete example, yes, does not.
Yeah. Yes. I think this is
Well,
lean
I understand that
itself.
you will see the why it fails, but maybe
Lean
some
itself can do it only in simple cases. For example, when you have something about natural numbers and it can, I mean, there is a tactic that tries to find a counterexample. Like just tries random natural numbers and see if they constitute a counterexample. In more complicated cases, of course, you can automatically construct the negation of your current goal. and then use AI to produce a counterexample. And I think I will not disclose any secret information if I say that our system can do it, at least in some cases, of course. Not like everything with AI, it depends on the compute budget and difficulty of finding a counterexample.
Okay. Misha. Миш, ты вроде руку поднял. Окей. Мы слышим какой-то шум, но не больше.
Yeah.
Okay, let me then ask a question, maybe to Arman and to you at the same time. So what our people like us see, that we see that there are several companies. Okay, we cannot. So there are some people in the company. The companies try to hire and to steal the key people one from another. So it should be in two cases. First, that they carry some very important secrets without which nothing is possible, and then hiring people is a way to stealing the secret. And second, which is more benign version, these people have some special abilities which allow them to be very efficient and to do something what other people cannot do. And the question is, assuming the second, what are these abilities and how people learn these abilities, or this kind of mystery. So what you should be able to do if you need to be efficient in this?
I am a bad person to
For
answer
you,
this
it's clear,
question.
you know lean, and you can, it's obvious why you are needed. But maybe you know, have
Yes,
some
I
idea
was
about
hired to
other.
do lean.
Yeah.
There is quite a lot of cost optimization stuff that's happening. So some infrastructure people are definitely needed.
Yeah, that's clear. But you
and
don't pay millions of dollars for salary for a person who can run a server, or I guess it's not something. It's
I don't know. I don't know salaries of other people at my company. I never asked them. My salary is definitely not $1 million
yeah,
a year.
yeah. But what can they do that you cannot? Can you say something?
They have some experience with training models.
So it's not some
etc.
mathematics. They are not expert in, I don't know, in convex optimization. This is not some formal logic. This is kind of experimental engineering experience with different models without any underlying theory. Yeah.
Yes, there is a lot of experiments and like experimental engineering. Yes. Arman?
Yeah, I think the second part, which takes not just a good programmers, and why some good companies want to hire a lot of good mathematics, for example, because the prize money, if you will create something like this, is really astonishing, and you want to have a lot of mathematicians working on your project, just because maybe you heard the story about some like you need to create a training data, and the quality of this training data become really important. All companies try to create just a lot of training data, just to put inside the training data all the text which we can find in the internet, and it was around the level of GPT-4, let's say. But after that, if you're trying to train the model, you need someone who is saying, okay, this response I like better than this one, or this response is correct and this response is not. So if you're creating the best tool for mathematicians to really try the edging stuff in theorems, you need someone who is capable to tell the stupid machine that this one looks good, or this one looks promising, or this theorem is actually solved in this text. Or so the second type of people who you want to like take from other companies is your ability to create a good group of mathematicians who will be able or to say, okay, this text we need to include, this text we don't need to include. Or you need to spend their time on accepting or not accepting the results of LLM after the first round of training. And like before that, you need to group this training data. So if you want to create the AI thing which will be able to decide, like there was a question about automation, how you will, without people, decide whether this is prove something or not. Right now you can't. Before, someone will create a very good model which with very good probability will solve that. You cannot do that. So you need to hire 50 mathematicians of very high-end level and try to ask them to please see these two texts and decide which one is solving this theorem and which one is not. If you're
it's clear that, of course, if you want to eliminate mathematicians and replace them with computer programs, for the beginning you need to have a test population to see what are they doing. This is clear. But my question was a bit about different things. Let me say it another way. So, of course, now people believe that this will be a big thing, and we need, I don't know, to prepare our students to live in the world of artificial intelligence and blah 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 blah. But the question is, what they should learn to be prepared? Is it any? Definitely, there is some knowledge now, but what kind of knowledge is on the level of education? Should they learn, I don't know, mathematics and convex analysis, or should they learn psychology and ego notion and whatever? What is its preparation now?
I would say that for most of the stuff you don't need convex analysis and whatever. There is much more of engineering stuff and of, I don't know, writing prompts, stuff like that.
Okay, but what course will you include in the for the first year students who will later do it? What will be curriculum for the first?
Unfortunately, my answer is probably that it's hard to predict because it changes so fast that it's hard to tell what will be useful in 5 to 10 years.
But what was useful for the people who are now leading the development? So it's probably known. What kind of education was useful for them?
I see that. Armand, do you want to say something about this? Or?
Yeah, but I was second after Alexander, so maybe Alexander will answer.
Yeah, but I wanted to ask just for the next question, so I guess you can.
Okay.
Yeah.
Okay, I will answer that. My assumption will be that one of the most important skills when you're talking with AI, as you can, for example, find in Anthropic Academy, which created some sort of academy for students to understand what's needed, is the skill to clearly explain what you're waiting for, the clearly
in natural language.
In natural language, you just need to understand what you're looking for. You need to have an ability to explain what will be the reasonable result of your session with AI. And so if you will imagine right now, if I will show you the picture, let's say there will be a monkey with a hat riding the bicycle, and after that I will ask you to recreate it with some Midjourney, let's say. There is a big chance that your first attempt to recreate it will be so different from the picture which you saw, just because you have never tried in advance to think about prompts in the style of image, prompts in the aspect ratio, prompts in the, I don't know, should it be photorealistic photo or something else. So I would say that somehow happened that right now is really important to abstract thing which you see and understand, is that important or not, how you need to describe it to other human or something. So when you're working with text models or with image models or with coding models, if you write prompt, I need the landing page where there is 2 buttons and users click on them and something is happening, you will be sometimes shocked how many ways to execute this task can be, and you will understand that, oh, I was thinking it will be 2 buttons, one on the left and one on the right, and the model is just created from one on top of another because you didn't explicitly say that. So I will say all the things which mathematics trained us to do, like pattern recognition, assumptions, logic, and so all this stuff which we were trying to learn without them, that still is important thing to do. The clarity of the message and so on.
Yeah, and at least for now, you need to proofread everything after the model.
No, you don't. I mean,
at least in programming.
In programming, you absolutely don't need to do that. You can.
If you don't insist on having a correct program, you can just try it. Okay, Sasha.
Okay.
Yeah.
I did write about 10,000 lines using Gemini recently, and it did some stupid mistakes when you have sufficiently complicated data structures.
We can make it as a contest, I suppose. The programmer who is vibe coding for more than 2 years now can easily set up the environment for this agent which will be coding, so it will write the correct tests. It will be the special document which will explain what you don't need to use any, and it will make it to run tests.
For me, it was faster to proofread. Than setting up all these. Okay, Alexander.
Yes. So my question was, so there are, I don't know, I guess like tens of thousands of papers about research papers about AI are published each year. I don't know.
What is written in all of them?
Yeah,
you cannot have so many
papers. And then there are AI companies, and I mean, is this in any sense? I mean, to which extent people and AI companies read these papers? And I know that,
or they just write them.
That all these transformers were from a paper. Attention is all you need. So at least in one cases it was useful, but maybe it's just a rare occasion, and I don't know. So maybe people just write it and then it doesn't go anywhere. Maybe whether an important ability to, like, I don't know, to work in a private AI company that doesn't disclose any information about its system is to actually read and understand what is written in that kind of papers quickly.
From time to time, you definitely need to skim through a paper. And for example, if your company decides to implement something that other company didn't describe in a paper, then yes, you you go over a paper and implement it on your site.
Okay, maybe you will not disclose anything if you, at some point, you can, I don't know, compile a list of 3 or 4 papers that some people in working practically in NI believe that they were useful for their work.
I don't know. One example that will definitely not disclose anything is when Google DeepMind did alpha geometry, they published code of the first version. They didn't open source second version yet, but in order to reproduce the results or build on top of it, you had to, or you obviously had to read the paper, read the source code, which was much less readable, and then use it somehow. I do not, I don't have better examples because I don't know what I can
Okay,
disclose.
maybe you can, another suggestion is, if Sasha will send you 3 papers on which claim to be useful for artificial intelligence, you can say what you think, whether they are just completely about other things and not useful, or maybe could be used for someone, or something is very important.
I have no opinion here. As I said, my expertise is much more in lean than in AI.
Okay, any other questions? So then I have a question. So it seems that what this theory, lean and cock, are kind of very strange theories based on some kind of intuitionistic type theory and so on, and blah blah blah. I don't really understand this, but that's what people said to me. And still, when people try to implement mathematics, it's quite and quite easy, in the sense that people do not say that, look, we proved our Fermat theorem in completely different formal theory. Does it mean that the choice of set theory and this language is kind of as historical coincidence, or maybe even a historical error? And if not Cantor, but if Martin Löf was before Cantor, then we will all happily live in constructive type theory, and we would consider this as a normal mathematics, and we have intuition corresponding to this. Do we need to develop some other intuition because the theory is different? How it works?
In some sense, it's much closer to programming, because every object has a type. So I would there are some theorems about embeddings that you can embed type theory into set theory and set theory into type theory. There are some provers that use set theory, like Mizar. But I would say that maybe for me it's much easier to think about type theory, because like you don't need all those tricks from set theory to build natural numbers. It's just an inductive type with 2 constructors, or
okay,
a function is just a function.
Let me ask more specifically. So now in our textbook for children's and first year students, we write something that the function is a set of pair, which is this and that, and there are sets, there are objects of the set, there are constructions of set, and so on. Can you imagine that in the next generations, you can imagine a kind of informal mathematics presentation when the functions will be explained differently, and this will be easier and closer to this programmer's way of thinking. There will be another intuition of what is an object, what is a set, not a set, but something else. So can you imagine such a textbook?
Yes, I can imagine it. I'm definitely not ready to write it. But I definitely can imagine it, and
so the counter-formalization of, I don't know, of a notion of function is somehow, you think, is a kind of historical choice, which is not that needed.
In some sense, yes.
But these new functions or new real numbers or whatever you will have the same properties, or only the important theorem will be the same, but there will be some difference in I don't know.
There is an embedding of type theory into set theory, and there is an embedding of set theory into
technically,
type
of course,
theory. So,
but maybe intuitive idea of real number will be implemented differently, and still maybe main results will be the same, but still this will be a different notion, more suitable for.
It's up to these two embeddings, it will be the same notion. It's just I mean, you define real numbers as, I don't know, for example, the quotient of Cauchy sequences or Dedekind sections or whatever you prefer, or decimal fractions. And the fact that you think about function as kind of a basic construction, a basic notion instead of these set with some properties, you can prove a correspondence that functions bijectively correspond to these sets. But you kind of the fact that you think about functions as basic notions doesn't change much.
Okay, no, because usually the people who work in programming have some kind of intuition of objects. For example, it's a basic notion, seems to be some kind of undefined, like set for us. They speak about objects, and they never can explain what it is for in such a way that I can understand it. But they have a very clear intuition, and even without formal theory. But maybe this is a sign of that there should exist a complete alternative foundations of mathematics based on some different notions, or you don't think so?
I am not very good at foundations, mostly because in the parts of mathematics I was working in, it was not very important. I see that the proofs that are accepted are the kind of proofs that I would accept the informal counterparts. But I have a reference. Mario Carneiro wrote his thesis exactly about the correspondence between ZFC and the type theory that is used in Lean.
Yeah. This is about formal connection. Yeah, but
yeah.
My question is different. Just if you say that there is a new textbook which use different tuition, I will be very eager to see it. Probably I'm to also learn this way, and I am spoiled already. But still, it's interesting to see.
I can imagine it, but I'm definitely not ready to write it.
And haven't seen something which can be
not
pretends
yet.
fill this ecological niche. I don't know how to say. Okay. Any other questions?
So there was a topic long time ago, but then there were many hands. So this why people who lead OpenAI and so on get million salaries. So what's their skill? And I think it's just engineering skill. So engineer needs to make a team of specialists work together and everyone knows something else. And then he built something very complex. So tuning language model for whatever purpose is like a delicate process. Many computers work together and there is a big team. And so you need to understand all the parts. And so, for example, Ilya Suchkever, he also he is responsible for scientific leader of OpenAI. For some time, he was like this. And so my guess is that on one, he is a good engineer, and second, he cannot come up with research plan to improve current system. And so what it means that he has idea of new algorithm that can improve things a little bit and then can do research to pull it through and have experience to understand what works and then gamble with real money on what works. I think.
Okay, but engineer, if you teach a mechanical engineer, there is quite clear what you should learn. Some basic notions of mathematics, basic notion of physics, kind of current technology or this or that. But if you this type of engineers, what kind of engineering training should they have on the first year of education?
What experience? So also I had to build a real algorithm that was supposed to be deployed in real life. And so there were some tests, and then algorithm is very complicated. So there were like 20 stages or something. And I was supervisor, so I need to understand several people. If they change one part, how it affects the other part. So I need to have really good thinking skills, understanding what think in advance. When I ask to make some change, I need to anticipate what happens 1 month later.
Okay, but what kind of course can be training for this?
So
just practical experience.
Well, so I will tell you. So there is a chain, maybe 100 assumptions. And so you don't know in advance which one will break. So you want to minimize what goes on and the chance that something goes on. And so you want to have as much mathematical insight in any single step. And so it's like very simple mathematical ideas I had to use all the time. And also there are unknown steps. So then there are different mathematical theories. And if they suggest to do something, if the different viewpoints suggest to do the same change, then it might be a good idea to try this change.
Okay, this is philosophy, but imagine you design a course for the first year students to develop this skill. What will be the homework for the
first? And then I will, like it's written in the chat, it's various statistical theories, like you had in your seminar, a VC dimension, but there is Rademacher complexity. So this is what I'm teaching, and it's just one window to see. And then there are books by Bishop about Bayesian reasoning, and there are probably other approaches to think about these models and to understand something. So just
so the thing that the theories about VC dimension are really useful.
No, they provide one view that can give a hint in one of the 100 steps, and there's the only thing that can maybe sometimes be a little bit indirectly useful, but there is nothing else. So, but I think just mathematical training in general, where you try to get some intuition about quantities of abstract ideas. Okay, it's too philosophical.
Okay.
So, but let me say, the company I worked for really wanted mathematicians,
No,
but
no,
all because of indirect skills.
Yeah, no. What are the reasons we can only guess? And this is,
Yeah, but also all these people who receive millions of dollars, many
no,
millions
we don't
of
sell
dollars.
mathematics education to anyone. Everyone
No,
here
they
is already
write
convinced.
mathematical papers about machine learning.
Yeah,
So.
Sasha, I think that all these people who got these millions were trained in more or less different but clear way. They were trained in some mathematics and some software engineering and all the standard courses in good universities with good professors and nice teams, etc. And if you just consider all what happened with them, it will not discover anything very special, very kind of graal given to them. But then they have their personal qualities and they have some good guesses for them. They have some good friends, etc. There are many circumstances, like in any other fields, like in finances. Some of these people in finances became, say, billionaires. Some others are, just clerks or whatever, just office workers. So I don't think you can discover anything specific. But the standard courses which are given now in artificial intelligence on based mathematics and software engineering are more or less the same. And it's helpful, like we are saying that things you learned or I learned in Moscow State University in mathematics, 90% of this, or if you need 80% of this, you will never use and forgot, of course, a lot of them. Nevertheless, we all believe that mathematical education is helpful in different ways, in different circumstances, etc. So it's just the same with AI. I don't think there is something very special here with these millions or whatever.
No, I think that there are kind of exercises which are useful, list of problems and so on, and it's quite possible that some kind of other things more practical or trying to experiment can be useful for the future people if they are trained in the first grade. Why not? First year.
I don't think that we have any evidence for this now, so it's kind of pure speculation anyway.
One thing that definitely can be useful, no, not in terms of what to teach in the first grade, but what can be useful is the ability to load some large model process that is happening and what should happen and how different parts should interact in your head and build it there. And I mean, doing this with some specific as I was told some time ago, asking whether something you learned in school about mathematics was useful for you in your real life is the same as asking if a dumbbell you were using in a PE, if you are still holding a dumbbell you were using in your PE class. It's probably like you are not holding the same dumbbell, but the
okay. Just
the thing is, when we are teaching, the exact exercises that we are given may be less important than hard to formalize meta skills we are teaching along the way.
No, just I'm asking very specific things. For example, if you need to train to be able to learn a lot of different things and to keep them in your head, maybe, I don't know, learning classical languages, Latin or Greek, could be even a better training than mathematics, because mathematics is kind of logical. You don't need to remember many things. And here you develop your memory skills and comprehension skills even better. No, it's not a joke. I just wondering.
No, in mathematics, if you, for example, if you need to read a paper and understand how different lemmas in this paper interact, things like that, this is a useful.
Okay, no, I'm not sure. For example, we had Andrei Muchnik, who was one of the most nice and clever people. He usually read just the statement of the theorem and then invented some way how to prove it. And then he looked here and there to see whether he does the same or not. So he doesn't need to remember many things. We still believe that mathematics is not completely useless. I agree, but still, I think.
Okay, I'm afraid that I need to go back to work.
Yeah. Okay. So we have 2 hours, so it's quite. But I hope we can have another session when you will демонстрация магии с последующим разоблачением, как сказал Булгаков, and probably if you agree, we will try to have this in some few weeks or months.
Okay, we will talk about it later.
Okay.
Now I need to go back to work.
Okay.
Sorry.
Ладно.
Bye.
Bye.
Thank
So
you.
now,
Bye.
Sash, maybe you can give and announce the next Kolmogorov. So today was not Kolmogorov seminar, but next week we will have Kolmogorov
next
seminar.
Kolmogorov seminar will be Arturo Merino from
Hamiltonian.
Well, from some university in Chile. He will be presenting results about Hamiltonian paths in 0-1 polyhedron.
This new proof of the existence of the Hamiltonian path of a convex hull of a subset of the vertices of Boolean cube. Yeah, that's what you said.
Yes, by edges of that, not the edges of the Boolean cube, but
the edges of the convex hull
of the corresponding polyhedron. Yes.
Okay, and this will be in a week from now, and it will be at normal time, which is 8:30 in Moscow, and maybe 1 hour. We should check whether this winter time is not changing.
6:30 in Moscow.
6:30 in Moscow, and corresponding time everywhere.
Yeah, that's the plan.
Okay, any other announcements or claims or заявления? Okay, then we finish, and we should thank Yura, but it's too late because he already left. Okay, okay.
Bye, everyone.
Yeah, I will try to put it in YouTube.